Attention now. Hello, everyone. I am Wang from Chuan University in Taiwan. Uh, Today, I want to talk about my study, which is titled on the effect of explainable AI on programming learning, a case study of urine gradient integration technology. Okay, just a moment. First, I would like to present some background on AI in education. I want to point out that the significance of AI-based learning technologies has several advantages, such as the enhancement of personalized learning experiences and real-time feedback and adaptive learning paths. And the AI-based learning technology can increase engagement and motivation among students. In addition, they support for diverse learning styles and needs. The second point is that there is a need for explainability in AI for effective learning. The importance of accurate predictions and answers from deep learning technologies can ensure reliability and trust in AI-generated outputs. And they can help students understand the reasoning behind AI recommendations. Therefore, the role of explainability in effective learning can be facilitating deeper comprehension of complex concepts or enabling students to learn from mistakes through clear explanations. Also, they can encourage critical thinking and problem-solving skills and reducing frustration and increasing confidence in learning tasks. This problem in this study is to handle the challenges in current AI-based learning technologies, including the high cognitive load on students and a need for improved learning outcomes. So the objectives of this study includes exploring this SAI technology to reduce cognitive load from students and improve the learning outcomes in the course called object-oriented programming education. So we have two research questions here. The first one is, how does the transparency mechanism for predicting code errors, which employs the gradient integration technology, impact the students' cognitive load? And the second one is, to what extent does the transparency mechanism for code errors influence students' learning outcomes? Here, I want to offer some backgrounds about explainable AI. Explainable AI refers to methods and techniques in AI that makes the output of machine learning algorithms understandable to humans. So the main goal of the SAI is to make AI systems decisions and actions more transparent, interpretable, and justifiable to users. There are three key aspects of SAI. The first is about the transparency, which means the SAI provides clear insights into how AI models process data and make decisions. And the second one, interpretability, means that it ensures that the decisions made by AI systems can be understood by humans in a meaningful way. And the last one, justification, means that the SAI allows the systems to explain their decisions, providing the reasoning behind each decision or prediction. So the importance of explainable AI can be, it helps students build trust in the AI systems. They provide accurate and reliable information. This explainability ensures transparency in how AI reaches conclusions. Also, it enhances students' learning outcomes because clear explanations can help students understand not just the what, but the why and how. It also improves the students' retention and application of knowledge. In addition, it also supports self-regulated learning for students because explainable AI helps in self-assessment and reflection. Therefore, students can identify areas for improvement and take corrective action. The last is...
Okay.
Okay, I will continue now. The last is promote the ethical use of AI because understanding AI decision-making process prevents misuse, and it also encourages responsible and informed use of AI tools. Now I want to present a brief overview of the technology called the gradient integration in SAI. It is a technique used to highlight important features in the input data that contribute to the AI model's decision. Specifically, it involves calculating the gradients of the output with respect to the input features. These gradients are integrated along a path from a baseline input, which is usually the little vector, to the actual input, accumulating the contributions of each feature to the final predictions according to the following formula in the screen. These integrated gradients are named visualizable because we can highlight the most influential features in the input data. Often we use the heat maps to make the students visualize the results of the SAI's computation. In the programming education field, this technique can highlight parts of the Java code where some errors are likely to occur, helping students in debugging and learning. So here is the research methodology of this study. First, we develop a deep learning model that can analyze Java code and make error predictions. And then we conduct a controlled experiment, which includes 36 students. And we use random assignment to control and experiment groups. Later, I will talk about the experiment design. in detail, which includes the task and the tools used and our data collection methods. About the data collection, we collect the data from a course at a university in Taipei, Taiwan, titled Object-Oriented Programming Design, using the Java programming language. The data sources include practices, assignments, exam questions, and collecting the code written by our students as the samples for training the neural models. Also, we include other online code resources listed in the URL here. And last, we conduct a human annotation of these codes to generate predicted code errors. Finally, we achieve the following annotation results, including 38 types of common OOP errors. And the training data set is of size 27,000, and the visualization data set is 42,000, 4,000, and the task data set is 5,000. Here is some common mistakes we found in the annotation process about object-oriented programming. For example, the first one states that the students does not establish right relationships between objects, such as object A owns another object B, or students does not use relationships correctly between objects, and so on. We have a total of 38 error patterns discovered in the data set. Next, we developed a deep learning model that was based on a performer architecture. Performer is a variant of transformer, which is more efficient and applicable in machines without too high resources requirements. In the following, I will explain the performer-based model and its functionalities in predicting code errors. And we will show how the gradient integration technique was integrated to the AI system to enhance its explainability and to investigate its impact on students' learning in debugging tasks. Here is the deep learning model we adopted in this study. As you can see, we fit the Java code as input to the embedding there, which includes content embeddings and the prediction embeddings. And then the encoder is a performer-based architecture, and which will provide the context embeddings for the next neural network classifier to make error predictions. Then these predictions will be used backward to generate the features or the attributions of each input feature that contribute to the prediction of the errors. Here's some information about the model training. We use 1,000 epochs for the training period. and the batch size is 64. The training and data set data ratio is 8 to 2, and we use ADAM as the optimizing algorithm. And the Java code vocabulary size is about 1,500, and the maximum code length is 1,000 characters. And the performer architecture parameters include the embedding dimension size of 32, and we use 8 headers, and the hidden dimension is 128, and the decoder number is 5. And the training results works very well because the accuracy can achieve as high as 99%. And this is the test website we developed for this experiment. In the leftmost screen, here is the window about the problem descriptions. Students can see the task. In the middle side, the window is the Java code editor, which students can edit the Java source code. And the rightmost window is the error predictions, which shows the output results of the deep learning models. And the students can also see the colored feature maps to identify which part of the code segments are most related to the error predictions. The darker green codes means the most relevant part of the code that the deep learning model think is related to the errors. With these tools, we hope to investigate how the SAI techniques can help students learn better. We conduct a controlled experiment with a control group size of 18 participants. And the students in the control groups were provided solely with only the error type predictions from the system. On the contrary, the students in the experiment groups can receive additional assistance from the system in the form of the code error explanations, which were represented as colored code segments. And the experiment process includes 4 steps. The first is the pre-test to assess the students' background knowledge about object-oriented programming. And then these students are assigned 3 debugging tasks of different levels of difficulties in a randomized order. And each student were required to solve the 3 problems with the help from the AI system. Then the students conduct a post-test to assess their knowledge after the learning process. Finally, all students complete an 11-item survey using a 5-point Likert scale. About measuring the cognitive load and the learning performance, we use a cognitive survey to measure students' cognitive load. And we use the online and pre-test and the post-test to evaluate their learning performance. As the data analysis method, due to the limited size of the participants and the observable departure from a normal distribution, so this study used the independent samples Wilcoxon-Mann-Whitney test to analyze the students' cognitive load and learning performance. The purpose of this analysis was to investigate whether there are significant differences in medians existed between the two groups of students. In the cognitive survey, we have 3 items about intrinsic cognitive load and another 3 items to measure extrinsic cognitive load, and the last 3 items to measure germane cognitive load. And we also include 2 open questions. The first is, how does the error type prediction feature provided by the system assist me in learning during the debugging task? And what are its drawbacks? The other one is, how does the code error location highlighting feature provided by the system assist my learning? And what are its drawbacks? And here is the content of the survey and the open questions. Now I want to present the results of this experiment. As concerning the cognitive load, we found that we will first present the cognitive load results and compared the results between the control and experiment groups under the statistical significance of p-values of 0.05. We also compare their performance in the exam scores under the same significance level of 0.05. And we will interpret the results to investigate the impact of the colored code segments on cognitive load and on learning outcomes. Here is the reliability of analysis results of the survey, and in the 3 constructs, you can see that we have a moderate level of internal consistencies across the dimensions of the cognitive load. And here is the independent samples Wilcoxon-Mann-Whitney test results. In this table, you can see that we have 3 results that are significant. The first is on the intrinsic cognitive load, and the last intrinsic cognitive load, and the last is on the post-test results. So the experiment group exhibited a significantly lower intrinsic cognitive load on the theme compared to the control group. However, there was no significant difference between the intrinsic cognitive load on error predictions. Nevertheless, the experiment group showed significantly lower intrinsic cognitive load on the topic content. About the results on extrinsic cognitive load, we found no significant differences in all the extrinsic cognitive load items. We also found no significant differences on the germane cognitive load. Concerning the results on learning outcomes, we found that the pretest scores showed no significant differences, which means that the background knowledge of the students are showing no significant difference. And the results on the post-test results show that the experiment group demonstrated significantly higher results than the control group. And here is some samples from the results on students' answers to the 2 open questions. I will go through the first example because of the time. Some students said, when I'm unsure of a mistake, error type predictions offer hints, but it can be challenging to grasp the meaning of the short text about the error types. So from the results of the analysis, we found that there are effective reductions in the intrinsic cognitive load on the debugging task with the XAI technique. And students could manage the cognitive load of the error predictions and the colored code segments effectively. So the error prediction generated by the model can offer students general guidance for code correction. But the students say that relying solely on these predictions may present challenges for them to understand. So in brief, the AI-generated colored code segments can reduce students' cognitive load and enhance learning outcomes. So this study found that the SAI techniques can reduce the cognitive load and improve the learning outcomes. And this study demonstrates an effective integration way of AI technology in education, hence providing scaffolding while promoting independent learning. Some future research directions can include conducting larger scale studies with diverse participant groups to validate the effectiveness of SAI techniques. And the second one can be exploring the learning support effect of other types of SAI tools, such as text generation, like ChatGPT, to explain code errors and code remediation suggestions. In addition, this is very interesting to investigate human-machine interaction to accommodate individual differences in learning styles and preferences is very crucial. And here is the end of my presentation. And thanks for your attention. And I'd like to answer questions if you have anyone. Thank you.